Radioactive dating. The decay of some radioactive isotopes enables the age of the object containing the isotope to be found. One of these isotopes is carbon-14 that enables previously living objects to be dated. Plants take in carbon in the form of carbon dioxide from the atmosphere through photosynthesis. Most of the carbon is the stable isotope carbon-12, but the atmosphere also contains some carbon-14. This is produced by cosmic rays, which free neutrons, which then collide with nitrogen nuclei, knocking out a proton to form the carbon-14. About 1 nucleus of carbon in 10 to the 12 is carbon-14, and this proportion is believed to have been constant for many thousands of years. However, there have been fluctuations recently. Plants, and animals as they eat plants, will have a similar proportion of carbon-14 while living, as carbon-14 has a half-life of around 5,700 years. When a plant or animal dies, it no longer takes in carbon from the atmosphere, or from its food, and so the amount of carbon-14 they contain will gradually reduce. By comparing the activity of the old sample with that of a modern sample, the approximate time of death can be calculated. Here's an example. A human skull is found to have an activity of 0.43 becquerels, whereas a recently deceased skull is known to have an activity of 1.57 becquerels. Calculate the age of the skull. Well, for this we can use this equation to find the decay constant, so rearranging, then putting in the values given. I'm going to work out the decay constant in years to the -1, though I could convert this into seconds. This comes out at 1.22 times 10 to the -4 years to the -1. Now I can use the activity is equal to the activity at t equals 0 at the start times e to the minus lambda t. Rearranging, I get this, then taking natural logs of both sides removes the exponential term. Rearranging for t, and then putting in the values given. The activity now is 0.43 becquerels, the activity at the start 1.57 becquerels, and this is my decay constant. This gives a time of 10,650 years. We can do a quick check. 2 half-lives would be 11,400 years, and would reduce the activity from around 1.6, 1 half-life taking it to 0.8, 2 half-lives to 0.4. This is slightly less than 2 half-lives, and we have an activity of slightly over 0.4 becquerels, and so our answer seems about right. Carbon dating can only be used for objects that were living. This includes wood, bones, and cotton. It cannot be used to date dinosaur bones, for instance, as they've been dead for far too long, and virtually all the carbon-14 will have decayed. Carbon dating measuring activity can give approximate dates of up to 60,000 years old, whereas direct measurement of carbon-14 content using a mass spectrometer can be used for small samples and can go back as far as 100,000 years for larger objects. It cannot be used to time a murder or even a date that a body has been dead for a few years, as the change in the activity would be negligible over a time of less than a few hundred years. Rocks containing uranium-238 can be dated through the decay to lead-206, with an effective half-life of 4.5 times 10 to the 9 years. This process is through a decay chain of several different decays, but there will be very few nuclei at the intermediate stages due to the much shorter half-lives involved in these stages. Assuming any lead would have been vaporized in the molten rock, there would have been no lead in the newly solidified sample. If a sample of rock is found to have a ratio of lead-206 to uranium-238 of 0.7, well, the number of lead to number of uranium gives 0.7. So we can say that the number of lead atoms is equal to 0.7 the number of uranium atoms. But initially the lead atoms were uranium atoms, so to find the number of uranium atoms on cooling, the number of uranium atoms at the start, we can say that N0, which is the number of uranium atoms at the start, will be the number of uranium we have now, plus the lead, which we've said is 0.7 times the number of uranium. So the number at the start is 1.7 times the number we have now. But we also know that the number now is equal to the number at the start times e to the minus lambda t. Rearranging to this, and then taking natural logs of both sides removes the exponential function. Now we can rearrange to give t giving this expression. But we also need to know the decay constant. And again, I'll find this out in years to the minus 1, coming out at 1.54 times 10 to the minus 10 years to the minus 1. We now have everything we need to put it into this expression, which I've done here, and this gives a time of 3.4 times 10 to the 9 years.